I've created this preface to the video on the normal distribution to help people who might have forgotten some basic elements of statistics appreciate the contents of the video, because the video does assume some basic knowledge. For example, this video on the normal distribution assumes that you already know three measures of central tendency, and in particular the mean. And if you already know what an average is, then you'll know what the mean is, because the mean is the term that statisticians use for the average. In addition to the mean, there's also the median and the mode. So these are basic measures of central tendency, and I assume that you understand in particular the mean already. I also assume that you know what a standard deviation is. And so just as a very brief refresher, a standard deviation is a measure of variability, and in particular it represents the average dispersion of data relative to the mean. So if you don't understand what a standard deviation is, I encourage you to check out one of my videos on the standard deviation or somebody else's videos on the standard deviation. The key thing to know about a standard deviation is it's measuring variability, and specifically it's the average dispersion of data relative to the mean. Now I also assume that you know what a histogram is. And just to refresh your memory, a histogram is a diagram that consists of rectangles. And each rectangle represents the number of observations associated with a particular value on the scale of interest. Now I'm going to show you an example of a histogram in a minute, but before I do so, I just want to mention two aspects of a histogram that are really important. First, an x-axis, which represents the continuum of the scale of interest from low to high, and the x-axis goes from left to right on the histogram. And there's also a y-axis, which represents the continuum of observations from 0 to some maximum. So here's an example histogram, and here are those two sides. I have the x-axis on the horizontal going from left to right, and here is the y-axis, which is vertical, going from 0 to some maximum, which in this case is 800. And this is the histogram of sleep. These are actual data from a real study. We can see that in this histogram, the range goes from 2 to 12 on the x-axis. And there's also a frequency axis, which goes from 0 to 800 frequency or observations. And here are the rectangles that actually make up the histogram. And so in this case here, 7 hours of sleep corresponds to something like 710. 710 people responded that they sleep 7 hours a night. And then on this little rectangle, it's something like 375, say. So each rectangle represents the frequency of observations in the data file that correspond to a particular value on the x-axis. The mean for these data is actually 7.31, and the standard deviation, the measure of average dispersion, is 1.21. So with knowledge of the mean, the standard deviation, and a histogram, you should be able to appreciate this video.
In this video, I'm going to talk about the normal distribution. I'm going to explain what it is by looking at an example of a very ideal normal distribution and some of the properties of that normal distribution. And then I'm going to give an example of a real-world normal distribution. Okay, let's get started. This is what a normal distribution looks like just with the normal curve. And this is where, if you look at it, you can tell that it has a bell shape to it, and that's why some people call it a bell-shaped curve. And people use the term bell-shaped curve synonymously with the normal distribution. Now, when people talk about a normal distribution, particularly within a standardized score format like z-scores, the middle, or the mean, or the median as well in the normal distribution, because they're equal, is often represented with a 0. And so a z-score has a mean of 0 and a standard deviation of 1. And if you're not really totally clear on z-scores or how to calculate them, I've got a video on that that I encourage you to check out. But I'm also going to talk about it here as well. So if you go in terms of standard deviations within a normal distribution, in terms of 1 plus standard deviation or 1 negative standard deviation above and below the mean of 0, you know for certain with a perfectly normal distribution that there are going to be 34.13% of the observations are going to be between 0, the mean or median, and in the normal distribution case, the mean and median are exactly the same. Between 0 and -1, you're going to have 34.13% of the scores. And conversely, between 0 and +1, you're also going to have 34.13% of the scores. So in total, you get 68.26% of all observations within plus or minus 1 standard deviation away from the mean. So the majority of people, in fact, a little more than 2/3 of people on a number of criteria, like height, like intelligence, a number of properties in the behavioral sciences and outside the behavioral sciences, most people are between 1 standard deviation below and above the mean. In fact, it's a little more than 2/3. Now, if you keep going further in the normal distribution, such as -2 and +2 standard deviations above the mean, you'll find that there's 13.59% of observations between -1 and -2, or +1 and +2. For a grand total, if you push out from -2 all the way to +2, you get 95.44% of observations between -2 standard deviations and +2 standard deviations within the normal distribution. And that's where 1.96, the value of 1.96 is very commonly used in statistics, in particular for a Z-test when you're testing the difference between a sample versus a population. We use a Z-test, and the Demarcation Criterion for statistical significance is a Z-score of 1.96. And that's because 1.96, which is just a little bit less than 2, actually corresponds to exactly to 95% of the total normal distribution. So there's actually 5% left over on the two tails for an alpha level test of 0.05. And that's where that 1.96 comes from. We could create a 1.96 here and a negative 1.96 here, and that would correspond to 95%, that section of the normal distribution. Now finally, the last sections that I'm going to talk about, because obviously the distribution is asymptotic, which means that the line just keeps going infinitely. In the last section of the most commonly used standard deviation demarcations in various disciplines, which is 3 standard deviations, we have 2.14% of the people or observations between -2 and -3, and then we also have 2.14 between +2 and +3. And that makes for a grand total of 99.72% of all observations in the distribution. And just like there is a correspondence between 1.96 and 95%, we also come across the value of 2.58, which is probably somewhere about here. So 2.58 and -2.58 about here, and that would correspond to 99% of the total distribution. And so if we needed to build 99% confidence intervals on a number of statistics, we would use the value of 2.58. Why? Well, it's because that value corresponds to that section of the distribution in order to represent 99% of all observations in the distribution. So that's what a normal distribution looks like theoretically, and this is what the Z-scores correspond to in terms of each section of the standard deviations and the percentage of observations in those standard deviations. Of course, any scores could be under here. You could have intelligence scores. It would be 100 and a standard deviation of 15. So 100 would be here, 115 here, and 130. And then we just keep going. 145 would be this section of the normal distribution. So very few people, if this was 130 IQ, 2 standard deviations above the mean is 130 for an IQ score. Very few people have an IQ score greater than 130. We can see that it corresponds to something a little more than 2.14%. There's another percentage here, and you can calculate that in your mind. It would be something like half of the 0.3, but it goes on infinitely. So very few people have an IQ greater than 130. It's only about 2 out of 100. Actually, I had that there, 0.13 on each side. What a normal distribution looks like in reality, this is data that were simulated from a computer program to generate normally distributed data with a sample size of 1,000. This is what it looks like. And it doesn't look perfect. There's a section here that looks like it's sticking out. You can tell it's just not that really smooth, perfect normal distribution. Now, had I created it with 10,000 people, it would look better. But in reality, this is what kind of data we get in practice. And you might be looking at that and you're going, well, is that really normal, or is it statistically significantly different from normality? And that's where we have statistics to help us test those kind of hypotheses in practice. So we've got tests like the Kolmogorov-Smirnov test, which I demonstrated in another video as well as the Shapiro-Wilk test. And in that video, I talk about how the Shapiro-Wilk is a better test than the Kolmogorov-Smirnov test. I encourage you to check that video out if you're interested. We can also describe the properties of a distribution with respect to skew, and in particular when it's non-normally distributed, well then we actually say, well, just how non-normally distributed is it? What kind of skewness does it have? And also kurtosis. Those are the two main properties of a distribution that we refer to when talking about non-normality. Is it skewed? Is it kurtotic? And there are different types of skewed distributions, just like there are different types of kurtotic distributions. But I'm not going to go into that in this video here. I'll make a future video talking about the various different types of non-normal distributions. Anyway, I hope you enjoyed this. Thanks for watching.